Hello, and thank you for joining me on this intergalactic journey. Tonight, we will slowly drift into the unseen tapestry of dark matter that threads through the universe. Imagine floating among distant galaxies, where invisible forces shape the stars and bend space around you. Feel the subtle pull of cosmic structures, the silent currents of mass that guide galaxies in their dance. As you drift, notice halos of unseen energy surrounding clusters of stars, the gentle hum of the cosmos whispering through the void. Let your imagination follow the pathways of the cosmic web, where each silent filament carries the weight of untold mysteries and possibilities. If you enjoy these relaxing moments, please consider leaving a like, subscribing, and turning on all notifications so you don't miss any of our future videos. But for now, just breathe. Let your body relax, release any tension, and allow your mind to drift. Let's begin. In the vastness of the universe, the gravity of unseen mass sculpts the delicate spirals of galaxies, suggesting a substance beyond ordinary matter, quietly orchestrating cosmic motion. Scientists call this invisible framework dark matter, a presence inferred from the bending of light, the swirling stars in distant galaxies, and the gravitational pull that keeps clusters bound, a shadowy architect shaping cosmic architecture without ever revealing its form or texture. Some theories propose that dark matter consists of particles that barely interact with normal matter, ghostly entities passing through planets and stars without resistance. Experiments deep underground and in orbit search for these elusive signals, yet every detection remains just beyond reach. This persistent invisibility has led researchers to imagine new physics, a hidden sector of reality that might explain the universe's missing mass, hinting at forces and fields we have not yet observed. Galactic rotation curves provide some of the clearest evidence for this enigmatic substance. Stars at the outer edges of galaxies move faster than they should if only visible matter existed, defying the expectations of Newtonian physics. This discrepancy suggests a vast halo of unseen mass, wrapping galaxies in a quiet gravitational embrace. The notion of dark matter emerges not from direct observation, but from the delicate dance of stars tracing invisible contours in space. Dark matter may influence the cosmic web itself, the vast network of filaments connecting clusters of galaxies. Simulations suggest that this hidden mass forms scaffolding along which ordinary matter flows, guiding the formation of galaxy clusters over billions of years. The universe's luminous structures, its bright galaxies, glowing nebulae, and radiant clusters, are thus shaped and held together by a material that remains intangible, revealing itself only in gravitational whispers. Some cosmologists speculate about exotic candidates like axions, near-massless particles that could form a cold, invisible fluid pervading space. If they exist, trillions would pass through the Earth every second unnoticed, a silent current flowing through our bodies and the planet. Experiments using superconducting magnets and resonant cavities attempt to detect the faint energy axions might produce, offering a tantalizing path to understanding a substance that has remained hidden since the universe's earliest moments. Gravitational lensing offers a window into dark matter's unseen architecture. When light from distant galaxies bends around massive clusters, it reveals not only the visible mass, but also the additional gravitational influence of unseen matter. These arcs and distortions paint a shadowy map of the universe, exposing concentrations of mass where no stars shine. Each subtle bend is a clue, visual fingerprint of dark matter shaping the cosmos with invisible hands. In some galaxy clusters, colliding clouds of gas and stars reveal the separation between ordinary matter and invisible mass. Observations suggest that dark matter does not interact electromagnetically, slipping through collisions unharmed while hot gas lags behind. This cosmic ghosting, visible in X-ray and optical imaging, offers a rare glimpse into the dual nature of matter, the luminous we see, and the unseen that rules the cosmos, an interwoven choreography of light and shadow. Dark matter may affect the formation of the first stars. Without its gravitational pull, gas clouds in the early universe might not have condensed into the first luminous bodies, delaying the birth of galaxies and altering the cosmic timeline. In this way, dark matter is not just a passive background. It is an active participant in cosmic history, a silent architect shaping the rhythm of creation long before life or planets ever emerged. The distribution of dark matter influences galactic collisions. When two galaxies meet, tidal forces stretch and warp their luminous stars, but the underlying dark matter halos pass through one another with minimal friction. This invisible framework can dictate the eventual shape of the merged galaxy, preserving angular momentum and subtly guiding the final formation. Each collision becomes a story written in gravity, revealing the unseen lines that structure cosmic evolution. Even within our own Milky Way, dark matter is believed to form an extensive halo. Its density increases near the galactic center, influencing the orbits of stars and clusters. While we cannot see it, astronomers infer its presence through careful measurement of stellar motion, tracing the unseen contours that govern the galaxy's dynamics. In this halo, dark matter silently orchestrates a gravitational symphony, holding the galaxy together across billions of years. The cosmic microwave background, relic radiation from the Big Bang, carries signatures of dark matter's influence. Tiny fluctuations in temperature and density reveal how early dark matter guided the clumping of normal matter. This primordial blueprint allows scientists to estimate the amount and distribution of dark matter in the young universe, connecting invisible threads to the luminous tapestry we observe today. Each faint ripple tells a story of unseen forces shaping everything we know. Simulations of cosmic evolution depend heavily on dark matter. By inputting its gravitational effects, researchers can recreate the large-scale structure of the universe, from sprawling filaments to voids devoid of galaxies. Without including dark matter, these models fail to match observations. Its unseen presence provides coherence to the cosmos, like an invisible hand guiding the growth of clusters and the arrangement of galactic neighborhoods over billions of years. The nature of dark matter might hint at entirely new physics. Some theories suggest self-interacting dark matter, particles that occasionally collide or scatter, creating subtle differences in galactic cores. Others propose hidden dimensions or modifications to gravity itself. Each idea challenges the limits of understanding, inviting us to imagine a universe where the rules we take for granted are only part of a deeper, more mysterious framework. Dark matter may influence black hole formation, subtly affecting the density of surrounding gas clouds. Its gravitational pull could accelerate collapse or shape the dynamics of accretion disks, indirectly guiding the growth of these enigmatic cosmic objects. While we cannot observe dark matter directly, its influence resonates through extreme environments, touching the most mysterious and powerful phenomena in the universe with a silent but persistent hand. In dwarf galaxies, dark matter appears to dominate, outnumbering normal matter by vast ratios. These small, faint galaxies provide laboratories for understanding its behavior, as their stellar motions are dictated almost entirely by unseen mass. Observations of these faint companions to larger galaxies reveal both the universality and diversity of dark matter's influence, hinting at patterns and variations that might unlock its elusive identity over time. Dark matter might even play a role in galaxy rotation anomalies, explaining why some spiral galaxies maintain nearly constant velocity curves far from their luminous centers. Its invisible halo prevents stars from flying outward, stabilizing the galactic structure. In essence, dark matter serves as an unseen scaffold, a cosmic net holding stars in place and allowing the luminous dance of galaxies to unfold without disintegrating into chaos. Clusters of galaxies reveal dark matter on immense scales. Surveys using X-ray and lensing data show that the luminous galaxies and hot gas contribute only a fraction of the total mass. The remainder, a hidden component, binds these colossal structures together. Each cluster becomes a testament to unseen matter's gravitational dominion, a quiet but pervasive presence anchoring the luminous cosmos and maintaining cosmic order on grand scales. Some physicists explore ultralight particles as potential constituents, forming wave-like structures that could smooth out small-scale cosmic fluctuations. These ideas offer alternative explanations for observations that standard dark matter models struggle to reproduce. The universe may contain layers of hidden complexity, with dark matter not only shaping galaxies, but also resonating across space as a subtle, undulating presence that affects the cosmos in ways we are only beginning to imagine. Despite decades of research, dark matter eludes direct detection. Deep underground laboratories, cryogenic detectors, and space-based observatories have yet to capture unambiguous signals. This persistent absence fuels both frustration and creativity as scientists design ever more sensitive experiments. It is a reminder that the universe contains realms beyond ordinary perception, where invisible forces silently dictate the structure and evolution of everything we see above the night sky. Invisible halos extend far beyond the luminous edge of galaxies, forming massive envelopes that bend light from more distant objects. Observations of gravitational lensing reveal intricate patterns, tracing unseen structures across millions of light years. These distortions allow astronomers to map the distribution of invisible mass, uncovering bridges of unseen matter connecting galaxy clusters like faint scaffolding stretching across the cosmos, its form detectable only through subtle cosmic signals. The first stars ignited within pockets of concentrated invisible mass, where primordial gas clouds collapsed under gravitational attraction. This hidden influence accelerated condensation, triggering nuclear fusion and the birth of light. The resulting stellar nurseries illuminated early cosmic filaments, creating patterns of brightness and shadow that hint at the underlying unseen framework. Galaxies were seeded within this invisible matrix, shaping the earliest luminous structures of the universe. During galaxy mergers, unseen gravitational halos pass through one another with minimal friction, subtly steering the resulting structure. Stars follow predictable paths shaped by this underlying influence, while interstellar gas clouds collide and radiate energy. Observations of merging systems reveal the separation between luminous matter and the massive halos that dominate total mass, offering a rare glimpse into the architecture governing cosmic evolution without any direct emission of light. Simulations suggest that on the largest scales, the universe resembles a vast web of filaments and voids, its luminous matter flowing along invisible strands. Galaxies are not randomly scattered. Their positions trace hidden scaffolding that dictates cosmic connectivity. These simulations closely match the distribution observed in deep sky surveys, reinforcing the notion that unseen mass governs structure formation and provides a consistent framework for interpreting galactic clustering across billions of years. Some researchers consider ultra-light bosons as potential constituents, forming wave-like patterns that smooth smaller structures. If present, these particles create interference patterns detectable in stellar motion, subtly affecting rotation curves and density profiles in dwarf galaxies. Their influence may reconcile discrepancies between observed galactic cores and predictions from heavier particle models, suggesting that unseen forces could operate at scales both microscopic and cosmic, shaping matter without direct interaction with photons or ordinary baryonic material. Stellar streams, remnants of disrupted satellite galaxies orbiting larger hosts, reveal the gravitational footprint of massive invisible halos. These elongated trails curve and twist as they traverse the galactic potential, mapping their underlying structure that cannot be seen directly. Detailed measurements of their orbits provide clues about mass distribution, offering a natural laboratory for testing hypotheses about the shape, density, and extent of unseen cosmic components in the environments surrounding galaxies like our own Milky Way. X-ray observations of colliding galaxy clusters show luminous gas slowed by electromagnetic interactions, while massive unseen halos glide through almost unaffected. This separation provides compelling evidence that the dominant mass component does not interact electromagnetically. By comparing the distribution of hot gas to gravitational lensing maps, astronomers can visualize the invisible matter-shaping clusters, revealing its influence on both large-scale structure and the dynamics of some of the universe's most energetic environments. Galactic rotation curves remain nearly flat, far from luminous centers, defying expectations from visible matter alone. This requires additional mass to maintain stellar orbits, forming extended halos that prevent stars from escaping. Variations in rotation profiles across galaxy types hint at differences in halo structure and composition, suggesting that invisible mass is not uniform, but instead varies in density and shape, subtly shaping each galaxy's dynamics, while remaining imperceptible through ordinary electromagnetic observation. Computer simulations recreate the evolution of the universe, showing that luminous matter flows along unseen filaments and accumulates in clusters. Without including these massive invisible components, simulations fail to reproduce observed galaxy distributions. The subtle gravitational influence provides cohesion, guiding galaxies to their eventual locations. Observing discrepancies between model predictions and reality informs refinements, helping scientists understand how the hidden cosmic framework governs growth, motion, and organization on scales, ranging from individual galaxies to vast superclusters. Certain hypothetical particles may interact only through gravity and the weak nuclear force, eluding direct detection despite forming the majority of a galaxy's mass. Efforts to detect them include sensitive cryogenic detectors, deep underground experiments, and astronomical searches for anomalous gamma rays. Each method attempts to uncover traces of interactions or decay products, providing potential windows into a realm of physics beyond the standard model, where invisible mass dominates the cosmos without revealing itself in any ordinary observable signal. Observations of small satellite galaxies reveal that some are dominated almost entirely by invisible halos, with stars contributing only a minor fraction of total mass. These faint companions serve as laboratories for understanding halo properties, providing insight into density profiles, halo shapes, and potential particle characteristics. Studying their dynamics and distribution allows astronomers to constrain models of unseen mass, offering a glimpse into the underlying gravitational architecture that dictates the motion of stars in these miniature cosmic islands. The separation of mass components in colliding clusters provides rare insight into invisible structures. While hot gas slows and radiates energy during interaction, massive halos traverse the collision almost unimpeded, dominating gravitational effects. Observing this difference allows astrophysicists to disentangle luminous contributions from the bulk of mass, offering a clear perspective on the forces that govern cluster behavior and emphasizing the critical role of unseen gravitational scaffolding in shaping the universe's most energetic encounters. Filaments stretching between galaxy clusters act as conduits for matter, both luminous and invisible. Galaxies travel along these bridges, flowing toward dense nodes where clusters accumulate. The gravitational pull from unseen mass within these filaments governs their motion, dictating large-scale patterns across millions of light years. Mapping these structures requires combining lensing, redshift, and X-ray data, revealing an intricate cosmic web in which invisible components guide the assembly of the universe while remaining undetectable by direct observation. The motion of stars in elliptical galaxies offers insight into their mass distribution. Unlike spirals, these galaxies have more random stellar orbits, yet their velocity dispersion indicates extensive halos of unseen mass. Studies combining spectroscopy and photometry allow researchers to estimate mass profiles, revealing that even in spheroidal systems, the bulk of gravitational influence arises from non-luminous components, shaping galaxy structure in ways not apparent from visible light alone. Early universe simulations indicate that halos formed before the first stars ignited, creating gravitational wells that funneled gas into dense regions. These wells determined the location of primordial galaxies, guiding the earliest star formation and influencing the subsequent distribution of luminous structures. By modeling the interaction between ordinary matter and these invisible concentrations, cosmologists can understand the timing and placement of early galaxies, linking the present universe to conditions shortly after the Big Bang. High-velocity galaxies moving through clusters experience gravitational friction from unseen mass, subtly altering their trajectories. This interaction stabilizes orbits, preventing chaotic scattering of galaxies within dense environments. Observations of these kinematics provide indirect evidence for the pervasive influence of invisible mass at cluster scales, showing that even galaxies themselves respond to an unseen framework that exerts control far beyond the limits of luminous matter. The formation of supermassive black holes may be influenced by surrounding halos, which help funnel gas and regulate accretion. Without these invisible components, the distribution and density of matter would differ, potentially delaying or altering black hole growth. Studying correlations between black hole masses, galaxy structure, and halo properties provides clues about how the unseen gravitational environment shapes the most extreme objects in the universe. Gravity-driven interactions between clusters over billions of years lead to subtle oscillations and mergers guided by unseen mass. Even voids, regions lacking galaxies, are shaped by the surrounding halo network, creating a cosmic tapestry of overdensities and emptiness. These large-scale motions, invisible in the electromagnetic spectrum, nevertheless dictate the evolution of structures, highlighting that the universe's vast choreography is governed as much by the unseen as by the luminous. Across vast cosmic voids, filaments of invisible mass guide the clustering of galaxies, forming an intricate web that stretches millions of light years. Bright galaxies trace these hidden threads, revealing their unseen influence. Observations suggest that luminous matter clings to a skeleton composed largely of dark matter, dictating the positions and movements of clusters and shaping the overall geometry of the universe without emitting any detectable radiation. The earliest star clusters ignited within regions of enhanced invisible mass, where gravity drew gas together with remarkable efficiency. In these primordial environments, pockets of high density served as cradles for stellar birth, shaping the distribution of luminous structures. Their existence illustrates how unseen gravitational forces subtly directed the architecture of galaxies before any significant radiation emerged, setting the stage for the cosmic hierarchy visible billions of years later. Gravitational lensing around massive clusters produces arcs and multiple images of background galaxies, exposing the contours of non-luminous matter. By analyzing the degree of distortion, astronomers can estimate the mass and shape of halos surrounding clusters. Each observation acts as a natural telescope, magnifying distant regions and revealing the hidden influence that guides cosmic evolution across scales, offering insight into the distribution of dark matter without ever capturing it directly. Stellar motion in dwarf spheroidal galaxies provides evidence for massive halos of invisible material. Stars orbit with velocities that cannot be explained by the luminous mass alone, indicating that unseen mass dominates these small galaxies. These faint systems offer critical laboratories for understanding the properties of dark matter, including its density profile, potential particle interactions, and the way it governs galactic dynamics in environments dominated almost entirely by non-luminous mass. Clusters of galaxies grow along dense filaments of unseen matter, which channel both luminous and non-luminous components into gravitational wells. This cosmic inflow shapes cluster structure, determining mass distribution, density, and alignment. Surveys combining X-ray, optical, and lensing data reveal that clusters sit at intersections of invisible filaments, highlighting the overarching role of non-luminous matter in shaping large-scale cosmic structure, connecting individual galaxies within a coherent gravitational network. High-resolution simulations of cosmic evolution show that invisible halos merge and fragment over billions of years, guiding the assembly of larger structures. Smaller halos coalesce into clusters, while some remain isolated, influencing surrounding galaxies through subtle gravitational effects. These simulations recreate observed distributions remarkably accurately, indicating that invisible mass forms the scaffolding for luminous matter, determining galactic arrangement, clustering patterns, and even the overall topology of the universe across immense scales. Gravitational interactions in merging clusters reveal that massive unseen components can pass through one another with minimal disruption, while luminous gas lags behind, emitting X-rays. This separation illustrates that the dominant mass does not interact electromagnetically, providing strong evidence for invisible halos. Mapping these systems enables astronomers to visualize non-luminous structures in 3 dimensions, revealing the framework that guides the motion and behavior of galaxies during high-energy cosmic events. The cosmic microwave background preserves fingerprints of early density fluctuations, which were influenced by invisible mass. Slight variations in temperature correspond to regions of over or under density, where gravitational wells eventually seeded galaxy formation. Analysis of these primordial patterns allows precise estimates of the proportion of normal and non-luminous matter, illustrating how unseen forces orchestrated the universe's growth from its earliest moments into the structured cosmos observed today. Observations of galaxy rotation reveal that stars at large radii orbit faster than predicted by visible matter alone. Extended halos of non-luminous mass prevent stars from escaping, maintaining rotational stability. These halos differ in density and shape across galaxy types, implying diversity in invisible matter distribution. Studying rotation curves provides critical insight into the unseen gravitational environment shaping galactic dynamics and the relative contribution of ordinary and non-luminous components. The formation of supermassive black holes may be influenced by surrounding unseen halos, which funnel gas inward and stabilize accretion. Without this additional mass, gas dynamics could alter the growth rate and final mass of these extreme objects. Observations of correlations between central black hole mass and host galaxy properties suggest that invisible matter plays a key role in regulating galactic cores, shaping the evolution of luminous structures at the smallest and largest scales. Cosmic filaments serve as highways for galaxies moving toward dense clusters, guided by the gravitational pull of massive invisible halos. These elongated structures influence both velocity and trajectory, funneling luminous matter toward intersections where galaxy density peaks. Mapping filament connectivity and galaxy flow provides insight into the large-scale structure of the universe, demonstrating that unseen gravitational networks govern motions across millions of light-years while remaining undetectable by direct observation. Dwarf irregular galaxies show signs of rotation and velocity dispersion that cannot be accounted for by stars and gas alone. Invisible mass dominates these systems, influencing orbital paths and the stability of stellar components. The detailed study of these faint galaxies informs theoretical models, helping scientists constrain the distribution, shape, and potential particle properties of non-luminous matter, while revealing its significant role in shaping galactic dynamics even in low-mass environments. Gravitational microlensing events occasionally reveal mass concentrations too faint to detect by other means. As background stars brighten temporarily due to an intervening massive object, astronomers infer the presence of invisible halos or compact structures. These rare events provide unique windows into the distribution of unseen matter, allowing researchers to probe the mass function of invisible components, detect substructure within halos, and refine models of how mass organizes galaxies and clusters on multiple scales. The pattern of satellite galaxies around massive hosts often reflects the influence of invisible halos. Satellites align along preferred axes, tracing the underlying mass distribution rather than random orbits. This anisotropy offers insight into the assembly history and shape of host halos, revealing how gravitational influence shapes satellite populations and guiding studies of mass concentration, halo triaxiality, and the interplay between luminous and invisible components in hierarchical galaxy formation. Observations of colliding galaxy clusters indicate that unseen halos provide the dominant gravitational binding, while interstellar gas slows, heats, and radiates energy. This behavior emphasizes that non-luminous components govern the cluster's total mass budget, dictating the dynamics of mergers. By comparing mass distribution derived from lensing with luminous tracers, astronomers can reconstruct the invisible architecture shaping cluster evolution and trace its influence across cosmic timescales. Rotation curves of low surface brightness galaxies show nearly constant velocities at large radii, signaling massive unseen halos enveloping these galaxies. The discrepancy between visible matter and gravitational influence indicates that luminous mass is only a fraction of total mass. Studying these systems helps constrain density profiles, halo sizes, and potential particle characteristics, revealing the universal role of invisible matter in maintaining galactic equilibrium and supporting the formation of extended disk structures. Stellar streams stripped from disrupted satellites trace the gravitational contours of massive halos, curving and twisting as they orbit host galaxies. Detailed mapping of these streams reveals density variations, halo shape, and potential substructure, providing critical information about the distribution of unseen mass. Each stream acts as a natural probe, offering a direct measure of gravitational influence where no light is emitted, unveiling the hidden architecture that shapes the motions of stars. High-energy observations of galaxy clusters highlight shockwaves and temperature variations in hot gas influenced by surrounding massive halos. While the luminous plasma reacts to collisions and compression, unseen mass continues to guide gravitational equilibrium. These combined datasets allow scientists to model cluster mass distribution with precision, illustrating that invisible components dominate total mass while directly affecting the thermal and kinematic behavior of baryonic matter. The formation and evolution of barred spiral galaxies may depend on surrounding halos, which regulate angular momentum transfer. Invisible mass influences disk stability, bar strength, and overall morphology, shaping stellar motion over billions of years. Observational surveys and simulations reveal correlations between halo properties and galactic structure, demonstrating that even subtle gravitational effects of non-luminous components can dictate the long-term development of visible galactic features. Galactic cores often reveal rotation and velocity patterns that suggest extended halos where unseen mass exceeds luminous matter. Stars near the center move under combined gravitational influence, but outer regions require additional mass to explain their speeds. These observations help map the shape and density of invisible halos, illustrating that galaxies are embedded in massive, unseen envelopes whose influence governs both stellar motion and the evolution of luminous structures over cosmic timescales. Some theories propose that invisible mass could form clumps of low-mass particles, concentrated in regions too small to detect directly. These microhalos may perturb stellar streams and subtly alter galactic orbits, leaving gravitational signatures. By studying these effects, astronomers gain indirect insight into the nature of dark matter, revealing that its influence can be both large-scale, shaping clusters, and finely detailed, sculpting stellar behavior in galaxies without any luminous counterpart. The distribution of galaxy clusters follows a non-random pattern, aligned along unseen filaments that span millions of light-years. Luminous matter traces these hidden highways, moving toward dense nodes under gravitational attraction. Observing large-scale structure through redshift surveys allows scientists to reconstruct the scaffolding formed by invisible mass, demonstrating that cosmic architecture is orchestrated by components we cannot observe directly, yet whose influence permeates nearly every aspect of galactic formation and clustering. High-speed stars on galactic outskirts serve as probes of extended halos. Their trajectories indicate gravitational influence far beyond the visible disk, requiring mass that does not emit light. By measuring stellar velocities and comparing with models, astronomers can estimate halo density, shape, and extent. These stars act as cosmic test particles, mapping the hidden framework that governs galactic stability and rotation, revealing the pervasive role of non-luminous components in shaping observable stellar motions. Observations of tidal tails from disrupted satellite galaxies reveal the unseen gravitational field of host galaxies. As stars are stripped, their paths curve along invisible contours, exposing the shape and distribution of halos. Detailed study of these features informs models of gravitational potential, showing that halos are often triaxial rather than spherical. The motion of these streams provides a natural experiment for understanding the architecture of invisible mass in and around galaxies. Massive elliptical galaxies retain hot X-ray emitting gas within extended halos. The retention depends on the gravitational pull of non-luminous components, which stabilize the gas against dispersal. Without this additional mass, energetic outflows could strip the gas from the galaxy entirely. Observations combining X-ray emission and stellar dynamics allow reconstruction of mass profiles, revealing that invisible halos dominate gravitational binding even in systems that appear dominated by bright stellar populations. Cosmic microwave background measurements reveal that unseen mass influenced the clustering of baryonic matter early in the universe. Tiny fluctuations in temperature trace regions where gravity pulled gas together, forming the seeds of galaxies. Detailed analysis provides precise estimates of invisible mass density, confirming that non-luminous components shaped structure from the universe's infancy. These primordial imprints connect the earliest moments after the Big Bang to the intricate network of galaxies observed today. Simulations of galaxy formation show that small halos merge to form larger ones, a hierarchical assembly that dictates cluster structure. Luminous matter accumulates within these halos, but the majority of mass remains non-luminous. The growth and interaction of these halos determine galaxy morphology, cluster richness, and filament connectivity. By comparing simulation results to observations, researchers gain insight into the unseen architecture that drives cosmic evolution on both galactic and supercluster scales. Gravitational microlensing, a occasionally exposes compact mass concentrations that are otherwise invisible. Temporary brightening of background stars indicates a massive object along the line of sight. These events can reveal substructure in halos, including potential clumps of dark matter or faint dwarf galaxies. By cataloging such events, astronomers probe the fine-scale distribution of non-luminous mass, offering constraints on particle properties and halo fragmentation that cannot be obtained through traditional electromagnetic observation. The motion of globular clusters around galaxies offers insight into halo profiles. Their velocities, orbits, and dispersion provide data on the unseen mass that governs their trajectories. Differences in velocity patterns between inner and outer clusters reveal halo density gradients. Studying these systems allows scientists to trace invisible structures in multiple dimensions, connecting local dynamics to larger galactic potentials and showing how extended halos stabilize and influence the motion of stellar populations over billions of years. Satellite galaxies often display preferred alignments that correspond with the orientation of invisible halos. These correlations indicate that gravitational influence shapes orbital planes and distribution. Observing these alignments helps reveal halo triaxiality, mass distribution, and formation history. It also illustrates that non-luminous components act as guiding structures, shaping the motion and evolution of smaller galaxies within a host's gravitational domain, linking the architecture of satellites to the surrounding cosmic framework. Colliding clusters produce separations between luminous gas and massive halos, observable through X-ray and gravitational lensing data. This phenomenon highlights the non-interacting nature of invisible mass compared with ordinary matter. Detailed analysis of such events provides critical constraints on the properties of dark matter, including its density, distribution, and behavior during high-energy interactions, revealing its role as the dominant mass component while maintaining minimal interaction with luminous gas. Low-surface brightness galaxies show extended rotation curves, indicating halos that envelop the visible disk. These systems are particularly sensitive to the gravitational influence of non-luminous components, allowing scientists to measure density profiles and spatial extent. By examining such galaxies, researchers can infer halo properties in environments where luminous matter contributes minimally, revealing the universal prevalence of invisible mass across different galaxy types and the consistency of its influence on stellar dynamics. Void regions expand faster than surrounding areas due to gravitational differences shaped by nearby invisible filaments. These vast empty zones illustrate how non-luminous mass organizes the large-scale cosmic web. Surrounding halos and filaments exert influence over matter flow, guiding galaxies into clusters while maintaining voids. Studying the dynamics of voids and their boundaries provides insight into how invisible components govern expansion, structure formation, and the balance between emptiness and matter accumulation across millions of light years. Tidal streams generated by satellite disruption act as sensitive traces of halo mass distribution. Curved stellar paths reveal the gravitational contours of their host galaxy, highlighting areas of higher density. Observing these streams allows measurement of halo triaxiality, mass substructure, and density gradients. Each elongated stream acts as a natural experiment in gravitational mapping, exposing invisible frameworks that dominate over luminous matter and shape the evolution and motion of both stars and clusters. The emergence of barred spiral galaxies correlates with the angular momentum of surrounding halos. Invisible mass can transfer momentum, stabilize disks, and regulate bar formation. Simulations show that variations in halo density and shape influence the strength and longevity of these bars. These insights reveal the subtle gravitational interplay between luminous structures and their unseen companions, illustrating that galactic morphology is deeply connected to non-luminous components sculpting stellar orbits over billions of years. Subhalos, smaller concentrations within larger halos, can perturb stars and gas in host galaxies. These structures, while invisible, leave measurable effects on stellar streams, galactic disks, and even rotation curves. Studying these perturbations allows scientists to infer subhalo distribution and density, providing clues to the particle properties of dark matter and the hierarchical nature of structure formation, revealing the fine-scale architecture of invisible mass woven into galaxies and clusters alike. Gravitational lensing of distant quasars occasionally reveals multiple images caused by invisible substructures in intervening galaxies. These anomalies indicate dense clumps of non-luminous matter, invisible through other observational methods. By analyzing image positions, brightness, and time delays, astronomers map the fine structure of halos, probing scales that illuminate both the distribution and potential composition of invisible mass, showing that even minute concentrations can shape the appearance of light across billions of light years. Early cosmic filaments directed gas and proto-galaxies into dense nodes, where the first luminous structures coalesced. These invisible highways guided matter over millions of light years, concentrating it into clusters and superclusters. Observing the large-scale distribution of galaxies today allows scientists to trace the unseen scaffolding that orchestrated early formation, showing how non-luminous mass influenced the very placement of the universe's first stars and set the blueprint for cosmic structure. Gravitational waves from merging black holes traverse halos of invisible matter, but the massive unseen components influence surrounding stellar and gas dynamics. While the waves themselves are unaffected, the gravitational environment shapes the growth and merger rates of black holes, indirectly impacting the population of luminous structures in galaxies. By correlating observed merger events with galactic environments, scientists infer the role of non-luminous mass in guiding the evolution of extreme astrophysical phenomena. Isolated dwarf galaxies show unusually high mass-to-light ratios, implying that their stars reside within massive halos of invisible matter. These faint systems provide unique laboratories for studying halo shapes, density profiles, and substructure. Observations suggest that while stars are sparse, gravitational effects dominate dynamics, revealing that invisible mass maintains orbital coherence, stabilizes stellar populations, and dictates evolutionary paths, even in the smallest galactic systems barely visible to conventional instruments. High redshift galaxy surveys indicate that non-luminous halos were already established early in the universe, providing the gravitational wells necessary for rapid star formation. Luminous galaxies trace these ancient structures whose properties influence clustering and growth. By comparing early universe observations with simulations, astronomers confirm that halos guided matter long before stars illuminated space, highlighting the invisible framework that enabled the development of galaxies and superclusters within the first billion years. Tidal stripping of dwarf galaxies as they orbit larger hosts exposes the contours of invisible halos. Stars and gas are removed along predictable paths determined by gravitational gradients, leaving elongated streams. Mapping these streams reveals halo shape, triaxiality, and density fluctuations, providing a direct observational probe of non-luminous mass distribution. The remnants of these interactions highlight the pervasive gravitational influence of unseen components across both galactic and intergalactic scales. The formation of ring galaxies may be influenced by collisions guided by extended halos. Invisible mass affects orbital energy transfer and tidal forces, determining the radius, morphology, and stability of the ring. By simulating interactions with non-luminous components, astrophysicists can reproduce observed structures, revealing that luminous interactions alone cannot account for these configurations, emphasizing the essential role of massive unseen frameworks in sculpting striking galactic forms. High-velocity clouds of gas within galaxies respond to the gravitational pull of extended halos, affecting infall rates, orbiting paths, and rotational stability. Observations of neutral hydrogen distributions show asymmetries and motions consistent with unseen mass. These clouds act as tracers of the larger gravitational field, revealing how invisible components regulate gas dynamics, star formation potential, and the redistribution of baryonic matter over galactic timescales. Cosmic simulations incorporating dark matter show that halo mergers drive the hierarchical buildup of galaxy clusters. Smaller halos coalesce, forming larger systems that funnel luminous matter into dense cores. Comparing simulation results with cluster observations validates the role of non-luminous mass in structuring galaxies across time. These models illustrate how clusters grow, filaments form, and voids expand, highlighting the unseen forces directing cosmic evolution at grand scales. Observations of high redshift quasars indicate that massive halos were already present to funnel gas into central black holes. These halos influenced accretion rates, shaping the early growth of supermassive black holes. Without such unseen gravitational wells, the observed early luminosity and mass of these quasars would be difficult to explain. This highlights the critical influence of invisible components in regulating the emergence of extreme, energetic structures shortly after the universe's first billion years. Ultra-faint dwarf galaxies orbiting the Milky Way exhibit stellar velocities, implying halos with extremely high mass-to-light ratios. These systems serve as probes for studying dark matter particle properties, density profiles, and halo extent. Observing these faint companions illuminates the universality of unseen mass across scales, showing that even in galaxies with minimal stars, invisible components dominate gravitational influence and shape their evolution over billions of years. Filaments connecting superclusters channel matter along preferred directions, influencing the growth and alignment of clusters and galaxies. These structures are dominated by non-luminous mass, guiding luminous matter into dense nodes and contributing to cosmic anisotropy. Mapping filament geometry and galaxy flow provides insight into the invisible gravitational framework, revealing how large-scale cosmic patterns emerge from the subtle yet pervasive influence of unseen mass across immense distances. High-resolution surveys of lensing arcs reveal substructure within massive halos, suggesting clumping or density variations in invisible components. These subtle variations affect the bending of light from background galaxies, providing natural laboratories for studying the fine-grained structure of non-luminous mass. By combining multiple observations, scientists can reconstruct halo complexity, shedding light on hierarchical assembly and the role of unseen matter in shaping gravitational fields across multiple scales. Dark matter halos can induce tidal heating in orbiting satellite galaxies, subtly altering stellar orbits and thickening disks. These gravitational effects leave observable imprints, such as asymmetric velocity dispersion and structural distortions, which provide indirect evidence for halo properties. By modeling these interactions, researchers gain insight into the density, shape, and particle characteristics of non-luminous components, shaping satellite evolution over cosmic timescales. As our journey through the invisible threads of dark matter comes to a close, allow yourself to sink even deeper into relaxation. Feel the universe's quiet rhythms surrounding you, the cosmic currents gently rocking your mind and body. Your thoughts slowly dissolve like starlight fading into the night, your muscles softening as you float weightlessly among galaxies. Rest here, fully supported in this vast and serene cosmic space. If you enjoyed this relaxing moment, please consider leaving a like, subscribing, and turning on all notifications so you don't miss any of our future videos. But for now, let your body relax, release any tension, and allow your mind to drift. Good night and sleep well.